Okay, so you just apply that. That identity is what allows you to break up the diagram from the blocks. So you apply that identity in both vertices, and so you get pictures like this, where now we have, in fact, 3 bulk propagators here, because I have the original one, and I introduced 2 more through those identities. And in this picture, so the y and y prime are integrated over geodesics, y1 and y2 are going to be integrated over all of AES at this point. That was the original vertex location. And then just using the fact that the bulk propagator is just the matrix element of the inverse wave operator, then you can do these integrals over y1 and y2 just by using this property. You can sort of break this up into a sum of 3 terms, each of which is some bulk propagator, but now with various dimensions. And so carrying this through, and again, it's actually quite elementary, you find that the original Witten diagram is expressed as a sum over 3 types of conformal blocks, with coefficients here that I'm suppressing, so those can be worked out explicitly. And so one conformal block is the exchange of the operator that was there in the original exchange Witten diagram. And then we have exchange of new operators with dimension delta m and delta n, which are the sum of delta 1 plus delta 2 plus 2m, or delta 3 plus delta 4 plus 2n. And so you get the structure, and in fact, this is precisely the structure you expect in a large N CFT. Okay? So these additional operators here, these are the so-called double trace operators. So if you have a large N CFT where correlator is almost factorized, there's a 1 over N expansion. And if you have 2 primaries, like O1 and O2, you can put them together and get the product O1 and O2. That gives you a new primary with dimension almost delta 1 plus delta 2. Or you can make additional primaries by taking O1, O2 and inserting even number of derivatives. Even number of derivatives keep it a scale. So you insert even number of derivatives, that kicks in these additional 2 dimensionality 2 now. Okay, so this gives you the precisely the conformal expansion you want. And indeed, you can check that this agrees with previous computations of this expansion that's done in more than 40 ways. Okay, and one output of this is then you get the OP coefficients for all the exchanges. And well, you can generalize this to sort of like scalar exchange to exchange of some spin L, and it's basically the same idea, except you use the propagator for that spin L field, and then you have to do a pullback of that spin L field to the geodesic. Otherwise, it's basically the same thing, and then you reproduce.
So the operators O can be anything?
Well, at this point, they have to be scalars. We've only worked it out for scalar operators.
But I was thinking, suppose you put a heavy operator, so that creates a semi-classical state. Wouldn't that geodesic become fat?
Yeah, I'm coming to that. So at this point here, yeah, they're not. At this point, there's nothing like that entering in because we're only dealing with the global conformal algebra. So there's actually no notion of heavy. So yeah, but this is coming. That's coming right now. Okay, so that story. Now I'll switch gears a little bit and talk about the case of the Sorta blocks and some questions.
Okay, it's good. The scaling dimension of the boundary of the whole operation.
Yeah, so you're right. So here, you can make it heavy, but heavy would be much larger than 1. Yeah. And so the formulas here are still they're exact in that limit. Everything will simplify in that limit, but
the difference would be fine.
You can do that, yeah. But so all I'm saying is I haven't made any restriction about that. So those things, my formulas still apply in that limit. Right? Okay, so now let's turn to the same story now in 2-dimensional CFT, where we have the Virasoro algebra. And again, the blocks in this case are much richer because, again, they're like an infinite number of global blocks, and they depend on the central charge. Again, no explicit results, no in general. Okay, but there's a lot of technology to attack these things. We have various approaches by Samologikov. And for example, there's a very well-known recursion relation that we worked out, and that allows you to efficiently compute a series expansion of the conformal block and an expansion where operators are becoming close to each other. So you can work out a finite number of terms. A series expansion, that's another important simplification occurs if you look at the regime of large central charge. Okay, so let's take central charge much larger than 1. And this, of course, is of relevance when in contact with total gravity and ADS. We're going with the semi-classical gravity ADS, and that, of course, is when the central charge is large. And so in this case, we're going to look at what you could call semi-classical blocks. So we're going to take the large C limit, and when we take the large C limit, we have to say something about what's happening to the operator dimensions. So if we just fix all the operator dimensions and take C to infinity, in fact, all that happens in that case is you just get back the global blocks. Okay, so that actually gives us back to the previous story, and there's a simple way to think about that from the point of view of ADS. So as you know, the central charge, when you go to ADS description by the Brown-Minot formula, basically becomes 1 over the Newton constant. Okay, so C is basically 1 over the Newton constant. And so taking C to infinity means taking the Newton constant to 0, which becomes gravity. And if you just keep your operator dimensions fixed, you're keeping your masses of your particles fixed, you say Newton constant 0, gravity turns off. And that is, in fact, the regime where you're looking at the global blocks. So you can think of the global conformal blocks as being blocks where we've turned off gravity. We want to do something where we get something new, we want to keep gravity. And so we should dial up the dimensions of some of the operators as we take C to infinity. And well, we can do that in various combinations. One thing we could dial up the dimensions of all the operators, and that's one limit you can look at. That's a bit harder to study, in fact. A very nice limit to look at is the so-called heavy light limit. And so that's where we're going to take C, and this diagram is actually mislabeled. This should be O2 here, and this should be O4 over there. So we'll take these guys to infinity, but we'll keep the ratio H1 over C and H2 over C fixed. And from the bulk point of view, that means that these guys gravitate by a finite amount. So they become classical gravitating sources. And then we'll take the difference between them to be fixed, and then also all the other operators will have fixed dimensions. Okay, so the reason for this is, even from the point of view just think about CFT, this is a useful limit to look at. But from the point of view of gravity, what this means is operators O1 and O2 over here are going to be gravitating particles, and then the rest of the particles are going to be like probes of that gravitating effect. So we can look at light probes probing some non-trivial gravitational background. Okay, so these, the versatile blocks in that limit were worked out by this nice paper by Fitzpatrick, Kaplan, and Walters a year or two ago, I don't remember exactly. And so again, we're after this whole block. Now, I've written this in terms of conformal cross ratio Z by using freedom to do conformal transformations to operators at canonical locations. And again, so this thing factorizes into a product of a holomorphic contribution and anti-holomorphic contribution. So we want to find these functions in this limit. Okay, so what these guys did is they did you could say a clever conformal transformation that effectively transformed away the heaviness of the operator. So they did this conformal transformation to use the fact that the stress tensor transformed by Schwarzschild derivative and sort of effectively transformed away the heavy part and then put it back in at the end. And so they're able to get a result from the heavy light block that was effectively written in terms of the global block. So they found this explicit expression in that limit. So what do these formulas mean here? So that again we have our front of hypergeometric function appearing. Like H12, this means like H1 minus H2. There's this parameter alpha appearing. Alpha is square root of 1 minus 24, the heavy operator dimension, divided by C. So if we get back to the global case, we would have taken alpha to be 1 because this factor would have gone away. But now alpha is non-trivial, and that also modifies the result. Okay, we'll see what the meaning of this alpha combination is shortly. Okay, and as we'll see again, this has a nice bulk interpretation, and I'm pretty motivated that. It's going to have an interpretation of geodesics, but now in backgrounds that are dual to the heavy operators. Okay. And we also want to explain what the exchange operator corresponds to. So, so the first hint of this was in fact in early paper, in fact, even before they worked out a general formula with the simpler case, Fitzpatrick, Kaplan, and Walters. Actually, first looked at the case where the heavy operator dimensions were the same, the light operator dimensions were the same, and large, and the exchanged operator was just the identity operator and all its descendants. So that means that's the vacuum block. So in your stored algebra, the vacuum block is non-trivial because the identity operator, you still get all the descendants of the products of series tensors. Unlike in the global case, where it's trivial. Okay, so to understand the results, what we did is we rewrote this not in terms of the plane coordinate z, but rather in terms of coordinates on the cylinder. So let's write z equal to that w, and if you take the formula in their paper and write the result of the conformal block, in this case, in terms of the cylinder coordinate, then you get this simple expression, just some sine function, that's alpha w, and the power here given by the light operator. Okay, what does this thing mean? So heavy operators, so the heavy operators are particles sitting in ADS. So if you have some heavy operators sitting at the origin of ADS like this, what does it do? Well, if it's, as long as it's not too heavy where it hits a black hole, it's not too heavy, it's create a conical defect. Okay, since again, there are no propagating degrees of freedom in theorems of gravity, everything is just global identifications. So this is equal to ADS with some redefined angular identification. Okay? And again, alpha here parameterizes the information about the operators. Okay, so so how do you get this formula then? Well, in fact, you just take a geodesic, 2 points on the cylinder, and you compute e to the minus ml, where L is the regulated geodesic length, and just do some elementary calculations, and you'll find that this expression is the square of this conformal block. Okay, with its mass is related to the dimension of the light operator. Okay, so that's a very nice result actually, because what you're seeing is some geodesic information about this non-trivial background, but just really emerging out of this basic CFT object. Okay. So, in fact, this is what sort of got me excited about this in the first place, being able to see some non-trivial geometry coming out of CFT, so we wanted to extend this in various directions.
Sorry, what is the deficit angle parameter?
Second.
What is the deficit angle parameter?
What is the deficit?
Yeah.
Yeah, so it's like 1 minus alpha. So if you can see here, if you look at this compared to this, and if we rescale rho goes to alpha rho, then we'll pick up an alpha squared, rho squared, so that here the angular, it's like 1 minus alpha. 2 pi times 1. Okay, so now I'm going to ask, so in this very simple case, this is the picture that gave us the block. Now we want to look at the general case and try to reproduce this expression here. But the basic ingredients follow from what I've already said. So we combine what I just said with the previous picture of global conformal blocks. And okay, so what do we have? So now, again, we have these heavy operators. We have heavy operators sitting in global ADS. So there's some whirl line there, and they're creating a conical defect. But there's more. We're going to have this exchanged operator in the conformal block. So that exchange operator is scalar. There's some scalar being exchanged, and so we're not going to look at the pure conical defect. We're going to dress up the conical defect by the scalar field. So we'll solve the scalar field wave equation on the background of the conformal, on the background of the defect, and the solution for that wave equation and normalized boundary conditions and so on ends up being this function, and geometric function. And so, okay, so now we have these light external operators corresponding to these light particles, now probing this conical defect that's dressed up by a scalar field. So we do kind of the obvious thing. We just integrate over the geodesic, and we weight it, integrate it, we weight it by the product of the bulk boundary propagators for the external points, and also weighted by this scalar field solution evaluated on the geodesic. So we have some integral over that geodesic, the natural integral, and if you plug in this thing here, you get this integral. And again, this is a pretty nasty integral. It's, you know, lambda. So we can look at the lambda dependence here. It's a geometric function. And this is where the graduate students come very useful. So if you put them to work, track the whip long enough, you eventually do the integral, and you can show that that integral is actually the square of some hypergeometric function, and this is precisely the square of that F coordinate. So we're getting the square of the conformal block here, which could be the full correlator, not just like the chiral half.
So this kind of limit you can only take for the ADS3.
Yeah, that's right. There's no version of the versorial block for.
No, I'm just saying like taking some of the operators would be heavy, let's say, if you get higher dimension, let's say, because in the ADS5 case, you are really dealing with a single trace operator. Then the scaling dimension is a large lambda limit goes like square root of lambda. I suppose the geometry itself goes like lambda. So you don't have a back reaction. Let's say if you take the two legs outside, it would be heavy.
Okay, but I mean,
It doesn't create a conical defect, that's what I'm trying to say.
Yeah, I mean, of course I can scale the operators however I want.
Yeah, but that would be multi-trace operation.
Well, but I could look at,
Yeah, I'm just curious if you can do it.
Well, I think I could consider things like that.
I'm not making it complicated.
I'm not going to get a convoluted defect. The fact that I get a convoluted defect is very special to
Right,
take that
right.
risk because I have.
Yeah. But do you kind of back, I guess the question is, do you also get some back reactive geometry that you calculate inside this?
Yeah, it's not clear what, I mean, you could consider a situation set like that in the bulk. It's not clear what that would mean in CFT. Yeah, it's very unclear because, again.
Or you look at a strong coupling region in the CFT. So
Yeah.
you just take, you are just taking a lambda.
Yeah, the question is what CFT object would capture this back reaction. So it's not a conformal block. The conformal block has no dependence on the coupling in it. The global conformal block is there's no dependence on lambda. Conformal blocks don't depend on lambda.
We saw the scaling that.
Yeah, that's right. But they only through the scaling dimension. That's right. All the dimensions would be sorted in that scaling dimension. Right. Okay, so yeah, perhaps.
Yeah,
Maybe it's possible. Maybe it's possible.
But even if you allow multi-traction, you get something like LLM somehow.
Yeah, that's what I'm
Geometry,
sure.
and then we have some issue on your node.
It's possible. Yeah, well, I'm just curious.
Yeah, that's an interesting question. Okay, now, yeah, so one other interesting thing that came up yesterday was, what if you make the operators very, very heavy? In fact, what if you make the operators heavy enough that the square root here becomes imaginary? So 24h over c becomes larger than 1. And in fact, that's precisely the transition where you expect the object to fall from a black hole. And so a black hole has a Hawking temperature associated with it. You can begin to see how that arises in these conformal blocks, because those versorial blocks were naturally functions of like either alpha w, where w is this coordinate on the cylinder. And so if alpha becomes imaginary, then this object, which was previously, was periodic, 2 pi periodic in phi, now it becomes periodic in tau. So with periodicity in tau, that's imaginary time, and of course, periodicity imaginary time associated with the temperature. In fact, you put things in that periodicity temperature is precisely the Hawking temperature. And so it looks like this heavy operator is producing something that when you probe it in this way, is looking like a black hole. And so this, in some sense, when you probe it this way, this pure state created with heavy operator is looking like the thermal state. And this is quite interesting. And again, this is discussed in the history. Okay, now let me, in the remaining time here, shift gears. Once again, talking a little more recent work. This is connected, but it's a slightly different application. And this is a way well, we'll think about here the high energy asymptotics of OPE coefficients in a 2-dimensional CFT. So this is some work that I did with Alex Maloney recently. There's some ongoing work that I'll mention briefly as well. And actually, this is a very simple idea we had here. We just want to generalize Carty's formula. When we generalize Carty's formula, where we look at not just the repetition function, that's what it does, but actually run that same logic where we look at correlation functions. So let's just do a lightning review here of Cardy's formula. So we're looking at the partition function, and for simplicity, let me just take a temperature and not separate left and right moving temperatures. And if you have a nice, compact unitary CFT that obeys all the nice conditions, then that CFT has a ground state, and the ground state is energy minus C over K. And so that from that ground state, we can get an approximation for the partition function of the low temperature limit just by saturating this trace with the vacuum state. And so we get this low temperature approximation for the partition function like this. At the same time, we have modular invariance, and so the partition function is invariant under beta goes to 4 pi squared over beta. And so this formula now tells us, after the transformation, tells us about the behavior of the partition function now at high temperature. Beta goes to 0. And then if we think of that high temperature partition function as a sum over states weighted by the density of states and the Boltzmann factor, then we get an asymptotic expression for the entropy S of E. And this, of course, is Cardy's famous result. And so this holds for theory. It's fixed central charge, E goes to infinity. And then there's this famous story, of course, with Strominger, where you notice that you take Cardy's formula, and then you use the Brown-Hanot formula to rewrite the central charge in terms of Newton's constant. Then this formula becomes nothing but entropy of the BTZ black hole with that energy. So BTZ black hole, entropy in that sense, emerges naturally for modular invariance in the CFT. Okay, so what if I run that same story now, but not looking at the partition function, but a correlation function? And for simplicity, let's just look at a 1-point function. So there's a very simple analog of this for higher point correlation function. Let's take a 1-point function. And so now we're not going to saturate this by the vacuum, because in the vacuum, if this is a primary operator in a CFT, all primaries with identity have a vanishing expectation value of the vacuum. So instead, we have to saturate this with the lowest energy operator that has a non-zero expectation value of that operator. So we call that state chi. So it's associated with some operator dimension delta chi, and therefore the energy of that state is delta chi minus C over 12.